So I do know that you are in for a treat tonight. But before my colleague, Professor Julie Davis, who is this year's topic director, introduces Dr. Grey to you, please allow me to make a few acknowledgements. Tonight's event is co-sponsored by the Department of Physics and Astronomy and also by Penn Sustainability, and we're grateful to both of them for their support tonight. The Wolf Humanities Center is generously supported by the Wolf Family Foundation, the Hershey Family Foundation, the Andrew W. Mellon Foundation, and the Office of the Dean in the School of Arts and Sciences. I want to offer warm thanks to our wonderful staff members without whom none of these lectures would happen, Sarah Varney, Sarah Malinsky, and our graduate student assistant, Juliana Barton. I also want to thank Professor Davis, whose brainchild this whole program and theme is. For our ASL interpretation program, I want to thank the interpreters, Dr. Jamie Fisher, the American Sign Language program in the Department of Linguistics, Pen in Hand, the Excellence Through Diversity Fund in the Provost's Office, the President's Office, the Penn Language Center, and the Office of the Dean in Arts and Sciences. Our goal with this public lecture series is to maximize public access to conversations that are research-based within and across the humanities. And we need your help in making that a kind of realized and ongoing project. If you see barriers to entry to this lecture series for our community, or if you have ideas about ways that we could reach out to other people, I would love to hear them. And what we know is that the best way to bring people into the university who would not come on their own is to bring them along. So I encourage you next time to bring somebody with you. And thanks for coming tonight. So here is Professor Julie Davis. Thank you.
Thanks, everyone, for coming out tonight. It's a beautiful sort of early spring evening, and we really appreciate you being here today. So about a year and a half ago, when we were thinking about the program that many of you have come to every time this whole year, thank you so much, but when we were thinking about that program and thinking about the ways that stuff inhabits our lives and defines our lives, we wanted to take up the question of the stuff we throw away. And that stuff is all around us, from the top of Mount Everest to the bottoms of our oceans. But since we humans have shared trash beyond our planet, on the moon and in space, it seems timely to think, too, about how much stuff we've left in space. And tonight's speaker, Dr. Stuart Grey, takes up this topic. Dr. Grey is a member of the Aerospace Center of Excellence in the Department of Mechanical and Aerospace Engineering at the University of Strathclyde. His research focuses on the precise orbit determination of space debris, in particular on how non-conservative forces affect the shape, attitude, and orbit of that debris. Dr. Grey received his PhD in aerospace engineering from the University of Glasgow, and he carried out postdoctoral research leading to a faculty position at the Space Geodesy and Navigation Laboratory at the University College London before moving to the ACE in 2016. I'm not going to share with you his many, many publications, but just simply move on to say that he is passionate about improving access to engineering education for low-income and hard-to-reach social groups, both in the UK and beyond. And he also leads the mechanical and aerospace components of the University of Strathclyde Engineering Academy, a scheme that offers an alternate route to university engineering education for students who would not ordinarily consider it. And I'm very, very excited that tonight we get this chance to talk about space debris. So please join me in welcoming Dr. Stuart Grey.
Thank you very much. Thank you. Tonight I'll be talking about the rubbish that we as humans, the garbage, rubbish that we as humans put up into orbit around the Earth. And I'll be talking through the process of how we've slowly over time accumulated all these objects, where they are, and what the future might hold for our access to space. So we'll talk about what space debris is. We'll talk about where it is, and we'll talk about if and how we can stop making more of it. So, once upon a time, we'll go back into our little fairy tale land. We have our Earth, a pristine orbital environment. Okay, no man-made objects there. This, once upon a time, was 1956. Okay? It's a long time ago. For some people, I talk to undergraduate students, and they just can't comprehend of the 1950s as an actual time when people were doing things. So in 1956, there were 0 objects in orbit. But we have to be more precise with how we're talking about things. There are 0 man-made objects in orbit. So when we're talking about space debris, we're not talking about meteorites and other natural things that are left over from the formation of the solar system. We're talking about things we put there. So there's a very definite delineation there. So 1956, nothing. 1960, 30 objects in orbit. And I'll pause here to explain the visuals you'll see throughout the talk tonight. So all of these visualizations are based on historical tracking data. Every object is an object that was tracked. It's in the correct orbit. So all the scales are correct, apart from the size of the objects. Okay? If they were that big, we'd see them, and I wouldn't have to talk to you about how scary space debris is, because we'd all be very scared of it. So the only thing that I've changed is the scale of the actual objects. Their paths and their locations, their orbits, are all based on the real tracking data. So objects are not to scale. I've got to reiterate that. People sometimes get mistaken about, well, if that's the size of Texas, what's the problem? So positions are to scale, paths are to scale, and that's important. We'll talk about their orbits, the path these objects take as we go along. So what do we see here? We see lots of objects kind of milling around, slowly moving around on this sort of scale. But in fact, these objects are moving very quickly. An orbit is very fast. Many kilometers per second the objects are moving. But they seem to be milling around the Earth, causing no real harm to people. We can see that they all seem to have different paths. And we can also think that these paths will change over time. So an object's orbit, it will have an orbit, the path it takes, but that path can change over time, sometimes quite dramatically when we're looking at long time scales, which we have to for space debris. So how do objects move in space? Well, in order to think about where objects are, we've got to go back to how these things actually move and why they move the way they do. So if we just get rid of the Earth there and we see these objects moving around, we're still not much clearer on what sort of paths they're taking. But if we focus on just 2, Sputnik 1, what started this whole thing off in 1957, and Explorer 1, the US response to Sputnik, let's say, in 1958, much to the disappointment of the US. So we focus on these 2 objects, and then we can think about tracing their paths. And we see they're actually following very predictable curved ellipses or ovals, and they follow the same path, and it repeats. They go over the same path again and again. And this is a real gift to us astrodynamicists in that it makes the maths quite easy. So it's all a big fake out that rocket science is hard. It's actually quite easy maths. Everything's just following these curves that repeat, and everyone's happy. What makes the curve it is? What determines the shape? Are the forces acting upon that object. And there's a number of different forces with 2 broad types. Gravitational forces, so forces due to heavy, massive objects being around us. They pull these objects and pull and push them. And non-gravitational forces, which might seem like a tautology, but there's a whole class of forces that move these objects that have nothing to do with gravity. And this is really important to remember with space debris, because over long time scales, these very small non-gravitational forces can have large effects and mean that our assumptions about the simple motion of these objects no longer hold. So talking about gravitational forces, the largest of these forces is from the Earth itself. So we can be lazy engineers. If we assume the Earth is a perfect sphere, the maths becomes really easy, because a sphere is the same, whichever angle you look at it, so you can work out the path an object takes on a sphere very easily. And the Earth is basically spherical, but unfortunately, it's not spherical enough. The Earth is actually squashed, we'd say squished in the UK. The technical term is oblate, but squashed is fine. It's basically wider than it is tall. That's because it's not a solid and it's spinning. So if you're on a merry-go-round, there's a force that pushes things out, so it's wider. The waist of the Earth is getting pushed out. And this change in shape means the orbits change. This shape of the Earth drags orbits around with it, which can mean over time different objects become dangerous to other objects. And on top of that, we know the Earth isn't perfectly smooth, but gravitationally, in terms of gravity, it's not very smooth either. This graphic here shows the intensity of gravity locally over the Earth. And you can see mountain ranges, you can see deep sea trenches, and the gravitational force felt by an object as it's flying over a given region of Earth differs. If we go to a different part of the world, we experience different levels of gravity. It's quite a small difference to us, and we don't really notice. We don't go floating off if we go to London or something like that. But it really affects the spacecraft. And we can also see what these changes are. We can see the North America here, South America. We can see mountain ranges, see the Andes. So things, large geographical structures, which are massive, like mountain ranges, pull objects and deflect these bits of space debris. We also have other bodies in the solar system that are tugging on our objects. And we have close by objects like the moon, obviously, which bends and shapes the orbits of these objects. But further afield, planets like Jupiter are so massive, they're very far away, but they are so massive that they also perturb or change the orbital path. So there's lots to take into account of different things pulling these objects and changing their paths over time. So that's gravity, okay, in its different forms, mostly due to the Earth, but other objects too that are big enough to pull our objects. Non-gravitational forces are where space debris work becomes very interesting. So the first key one, and the most important force when it comes to space debris and having a chance of avoiding a catastrophe, is drag. So this is a force on an object as it is ploughing through the atmosphere, Earth's atmosphere. So Earth's atmosphere doesn't just stop at any given point, at a few miles or 100 miles. It slowly peters out. So even objects in quite high orbits experience some drag. When they hit molecules of the atmosphere, it slows them down. This slowing down means the altitude of the object falls, which means it hits more, which means it falls some more, which means it hits more. And this sort of runaway effect means that eventually most objects in low altitudes will burn up in the atmosphere, which is a good thing. This video, by the way, is from the re-entry of the Orion capsules. This is a video of something re-entering. Those flames are just because of the speeds involved in these objects and the friction forces caused. Generates a lot of heat, and flames melts objects. So a lot of objects will just burn up, which is a great result. The other one is a little bit different, and this is solar radiation pressure. Now, this is the force of the light from the sun hitting the objects in orbit. And you might think, but how does that move an object? So Einstein says that while photons, pieces of light, have no mass, they do have momentum. So if a bit of light, a photon, hits you and bounces off, there is a small push. Right now, from these lights, from this screen, we are all getting pushed by these photons. It is an absolutely tiny force. In our day-to-day lives, we can't feel it. But in space, where there's nothing else there to push back against, there's no atmosphere, these small forces build up and can push these objects, and over decades or hundreds of years can radically change where their orbits take them. So that's what's going into the orbits of objects, where they are going, and hopefully we can work out where they're going to go to. But where is space debris? So we want to get a feel for where this stuff is in relation to us. So we'll talk about a few orbital regimes. And the first one we'll talk about is low Earth orbit, very imaginatively titled. And these are objects close by the Earth. And we generally say that low Earth orbit is anything with an altitude less than 2,000 kilometers. So this white box here is up to 2,000 kilometers altitude. So the vast majority of objects we put into space go into low Earth orbit. All the space stations, all the shuttle missions, Hubble, a vast majority of scientific missions all go to low Earth orbit. The only manned space flight ever to leave low Earth orbit were the Apollo missions. Okay, so the vast majority of our operations in space are in this region. And we'll see as we go through time it really filling up, and you can see why we define it the way we do. So here we've defined an orbital regime by its altitude. So we can say it's in low Earth orbit if the altitude of the object is less than 2,000 kilometers. But to complicate matters, an object's altitude in orbit isn't always constant. So we can see an example. So we look at Vanguard 1, which is the first solar-powered satellite going around the Earth. And if we look down on its orbit and trace it out again, we can see that it goes very close to the Earth down here and further away up here. Okay, so all orbits aren't circular. They're elliptical. And sometimes they're far away from the Earth, and sometimes they're coming very close. This is called an eccentric orbit. And you can get highly eccentric orbits, or orbits that are just a little bit eccentric. And we like that in the UK. We like our eccentricity. So back to our view of 1960. We now know a little bit more about how these objects are moving. We've got our 30 objects in 1960. So what, in 1960 as a snapshot, before it gets too busy, what are these things? So all these pink objects are debris, but what do we mean by that in this context? So we can subdivide that to the green objects, which are rocket bodies. So in order to launch an object into space, we typically use a multi-stage rocket. And the upper stages, so the fuel tanks and boosters, are jettisoned and stay in orbit. So basically it's large fuel tanks careening around. They're about the size of a city bus. You do not want to be encountering one of those in orbit, I'll tell you that. And but they're very easy to track. They're so big, you can, with the radar, you can see them a mile off. Okay. We also have in the yellow dots here dead satellites. So before Vanguard 1, which is solar-powered, and still a vast majority of satellites were battery-powered. And when the batteries ran out, the laws of physics didn't stop working. They kept going in their motion, in their orbits. They just weren't working anymore. We call these dead satellites. This also occurs when there's a mechanical failure or an electrical failure. The satellite will keep following its path, whether it's working or not. This is important. The fragments, so things falling off satellites hitting together, causes new pieces. They're also separate objects. And mission debris, which is a very small section, a small number of objects, a very interesting one. These are bits of debris generated through the normal operation of space missions. An example would be on something like a space telescope, the lens cap. You cover it up, you launch it, when you get into space, you pop that lens cap off. That lens cap becomes space debris, that's mission debris. Another type of mission debris are tools like wrenches and hammers that have been accidentally let go of by astronauts on spacewalks. And you can see videos of astronauts accidentally letting go of a wrench and then trying to reach for it, and it's gone, and then it just slowly moves away in its own orbit. They eventually do deorbit themselves, but there are a small number of hand tools in orbit around the Earth. So why isn't all this stuff raining down on us? Why aren't we just constantly seeing big holes in the road? Okay, it's a good question. A lot of people are like, okay, you're just making this up. And the reason is the atmosphere, that drag. These objects in low Earth orbit are moving about 7 kilometers per second. Okay, so that's 5 or 6 miles a second. Incredibly fast. And the friction caused when they enter the atmosphere burns them up. If they're metal, it just melts them and nothing left. Okay, which is great. And that's why things aren't just falling down all the time. Objects are burning up on a very frequent basis. So as we'll see, it's very busy up there, but very few of them reach the ground because they all burn up. In order to survive that re-entry, you have to be either very big or designed to survive that. That's why the space shuttle is designed in the way it's designed, okay, to survive those incredible temperatures and speeds. So intact re-entry is extremely rare. So something accidentally re-entering and landing on us is very, very rare occurrence. And if something does make it to the atmosphere, the majority of the Earth is oceans, lands in the ocean, splosh, we're happy. Or it'll land in the forest or somewhere like that. The chance of it landing in a built-up area are astronomically small, let's say. So a related question is, anyone in the audience from Wisconsin? Anybody? Okay. So what we learn, a lot of the work here is on probabilities, and you learn that very unlikely things happen. Okay. Sputnik 4 crashed into the high street of Manitowoc, Wisconsin in 1962. The height of the Cold War, everyone went absolutely crazy. As you can imagine, put yourself in their shoes. There's a little plaque. Sputnik 4 satellite fragment was recovered at this site September the 6th, 1962. So you can imagine the scene of people going about their daily business, and then suddenly something appears to come from the sky. It's smoking. It's covered in Russian writing. They were not taking it well. Okay? So rare things do happen, and sometimes things do re-enter. But Sputnik 4 re-entered because it was a test for some of the first manned missions. It was designed for re-entry. It was built very strong, so that's why it made it through the atmosphere. It was not aimed at Wisconsin. Okay? That's just a fluke. I'm sure the USSR were very happy that it happened that way, but there's no planning involved with that. And it only survived because it was made very strong and tough to survive that re-entry. Okay, so we talked about what space debris is. Non-useful, man-made objects in orbit. It's wordy, but accurate. Dead satellites. Satellites that are broken, or run out of batteries, or have had some sort of failure. Spent rocket stages, those big empty fuel tanks that are still going around up there. Mission debris, those lens caps, those wrenches. And fragmentation debris. The pieces of debris cause when two objects hit each other and create more objects. And this is where things get much more interesting nowadays. So in 1962, we jump to 300 objects. Looking a lot busier now. And we also see the UK's first satellite. So there's going to be a little bit of a UK slant to this. I hope you indulge me. Called Ariel 1. And we like our Shakespearean references. You know, we try and go over the top on these things as much as we can. But launched by the USA. Right? And this is an important question because whose responsibility then was Ariel 1? If Ariel 1 crashed into something, who's to blame? Okay, we the UK built it, but the US launched it. Who has ownership and who has liability? And these are questions that are still not being answered. And a big issue with space is that it's a shared resource. It's a commons. And how we all use it and the rules and the laws governing it are still in flux to this very day. 1965, 800 objects. Now, it's important here to say that these objects are objects that can be tracked by radar and viewed by telescopes. So these are all objects bigger than about a grapefruit. Okay? So when I'm saying 800 objects, there were many, many more than 800, but these are the ones that could be tracked. So things about grapefruit size, so 10 centimeters cubed or bigger. So 800 trackable objects in 1965. And things are starting to get a little bit busier. We can zoom out a little bit. And we can also see the first geostationary satellite, just down there in the bottom, called SYNCOM-1. And this was a new use for space. And if we trace its little path, we can see that it's a perfect circle. So not eccentric at all. And it's quite far away. And you might wonder, what is the point of this? This orbit is chosen because the time it takes to do one orbit is exactly the same as the time it takes for the Earth to do one rotation. This means that if we plot this object at the equator, from our point of view, looking in the sky, it's still. It's static in the sky. So that means we can point our satellite dishes and just have them fixed looking. So this is for communication satellites. All of our satellite infrastructure is really based around these geostationary satellites, which can from our point of view, to sit there in the sky. We can beam up information, get it back down somewhere else. This is the backbone for our modern communication networks. If the altitude was slightly higher or lower, it would not match the rotation of the Earth, so it would move around in the sky. So it's got to be exactly the right altitude. This is prime real estate. And in order to use it, to put your multi-billion-dollar communication satellite there, you've got to apply for a slot. If you get given a slot, you've got to stay in that slot, you've got to stay in that box and not move out of it under any circumstances. It's all very controlled. So the second orbital regime is geostationary orbit, or GEO. And this isn't a range, this is a precise circular orbit at 35,786 kilometers altitude. Any higher or lower, and it'd be moving in the sky. But at that exact altitude, it's static. So fast forward to 1971, 2,500 objects in orbit. We can see Leo getting busier. And Prospero 1, anyone guess which country might have? We're still at it. We're still trying. So this was another UK satellite. Okay, this time launched by the UK in 1971. And something to remember is that the US and the USSR weren't the only game in town, and especially not the only game in town now, but the UK had its own capability to launch satellites in the 70s. And we have the dubious honor of being the only country in history to have the capability to put things in orbit, only to give it up. I'm not sure that's a good thing or not, but we decided we're not bothered. So the Black Arrow rocket, which looks suitably angry there with its big mouth open, this looks a lot like a missile. And that's because all of the technology around getting things into orbit is the same technology you use to build a nuclear missile. Okay? A nuclear missile aims to put a warhead in orbit in order for it to drop on an enemy's territory. So this is all inextricably linked. All of this effort of putting things into orbit was linked with the military and the desire to build weapons. That's why the UK was involved. So Prospero didn't go well, right? This is one of the reasons we might have given up this. So one thing I like is there's a quote given by an official quote on why it went wrong. And you can imagine some civil servant going up to a prime minister and saying this. The Black Arrow's final stage rocket entered orbit rather too enthusiastically. That's not a technical term, that's just... Yeah, so it's overshot massively, it went into a crazy orbit and all went horribly wrong. So we sort of put our hands up, we're not going to carry on doing that. We'll let the US do what they're good at. So in 1978, 4,500 objects in orbit. So you can see the real change here as we go through the time. If we zoom out, we can start to see some objects in that geostationary ring. You see objects, these satellites are there at that given altitude, so they're above the countries, giving communication links down to them. We can see a new object there, which is in between geostationary ring and low Earth orbit, called Navstar 1. And this was the first satellite in what would become GPS. Okay, so we wander around new cities. I wander around Philadelphia, staring at my blue dot, trying to work out how to get places. That positioning capability all comes from space-based assets. So the first of the GPS satellites was launched in 1978. And this is where we talk about our third orbital regime, the medium Earth orbit, or MEO. And that's everything in between the geostationary ring and low Earth orbit. And here we can see the GPS constellations in pink and the Russian equivalent of GPS, GLONASS, in yellow. And we can see they follow very definite structures. This is to make sure whenever I'm walking around outside, there's always a few satellites above me to give me the signals I need to position myself. These are about 20,000 kilometers altitude. By 1986, 6,000 objects in orbit. And we see one very close to the Earth, that's the Mir space station. And something to remember is space stations are really close to the Earth. It costs a lot of energy and effort to get anything into orbit, and the bigger the thing you want to get into orbit, the closer you want it, basically. Space stations are so close to the Earth that you have to be constantly boosted. The altitude has to be raised to stop them burning up. International Space Station has to be regularly boosted up in order to stop it burning up in the atmosphere because they're so close. International Space Station at about an altitude of 400 kilometers. So what causes debris to deorbit? Objects slowed by an atmospheric drag will eventually burn up. And objects pushed into lower orbits by other forces, for instance radiation pressure, will also burn up. So you can start by touching the atmosphere, and then your card's marked. Or you can start in a nice orbit, which is slowly pushed until you start grazing the atmosphere, and then, again, the process of re-entry begins. By 1990, we've got 6,500 objects in orbit. And it was at this point, finally, people realized there might be a problem. Okay, so we've got to this point of, oh, okay, hold on, there's a lot of stuff there. If we keep on going at this rate, there's going to be we're going to start removing people's access to space. It's going to be too dangerous to launch things. So there's activities to reduce the amount of new debris created. Okay, reduction in creation, not removal, but just trying to stop putting new things up there. So one thing you'll notice, and the last sort of area we haven't really covered, so we've covered LEO, which you can see very clearly now. Now it's full up. You can see the geostationary ring. We're looking at it from the side. You can see medium Earth orbit. But there's all of these satellites above the northern hemisphere. And these are objects in Molniya orbits. So Molniya 324 is an example. If we look down on its orbit, we can see it's in a highly eccentric orbit. It starts very far away and comes in very close to the southern hemisphere and then goes back up the top. So it spends a lot of its time over the northern hemisphere, and that's because these are used for communication over the poles. Ideally, we want to use geostationary satellites, but as you get to higher and higher latitudes, your angle of being able to see them gets worse and worse. So if you are interested in communicating over the Arctic, or things happening over the Arctic, for instance, if you are the US or Russia, you make sure you have assets in these special orbits. So that's why there's lots hanging around the northern hemisphere and not the equivalent, because no one really cares. No one's fighting over the South Pole yet. By 1998, 8,800 objects in orbit. The Hubble Space Telescope, one of them. And you've all seen the images from Hubble, these fantastic images of the deep universe. Absolutely brilliant mission. One of the benefits was it was in low Earth orbit. It was put there by the shuttle, and shuttle missions could go and repair it and upgrade it. So there were problems with the optics initially, with the glass. They fixed that. As digital camera technology got better, they could replace and upgrade the sensors. And when things went wrong, when there was power drops and things like that, they could go and fix it. We can see what a space debris impact looks like by looking at some of the objects removed from Hubble when it was being repaired. So this is a picture of a solar panel that was broken, taken from Hubble. And that looks, for all intents and purposes, like a bullet hole, basically. It looks like someone shot it. That sort of damage is caused by a very small piece of space debris. Because these objects are moving so fast, they have a tremendous amount of kinetic energy. And something the size of a paint fleck or a small grain of sand moving at 7 kilometers per second has the same kinetic energy as a high caliber rifle bullet. So this would be a very small object hitting that solar panel, just goes straight through it. So anything bigger has much more energy. So anything the size of our grapefruit hitting a spacecraft would be absolutely catastrophic. These are very small objects moving very quickly that cause this damage. The space shuttle was also damaged. These are pictures of their windscreen at the front of the shuttle, which is many inches thick, an incredibly strong structure. Big chunks were taken out by impacts. These are photos of when the shuttle returned. They didn't go right through the windscreen, luckily, but were enough to very highly worried astronauts and ground control about what was going on. So later in the shuttle's lifetime, it was actually flown backwards. Once it was in orbit, it was turned around 180 degrees, so it was moving this way. So any debris, or most debris, would hit its rear, hit the boosters, which aren't needed for a safe return to Earth. The windscreen is needed for a safe return to Earth. The boosters are not. The space shuttle glided, sorry, past tense, sorry, I'm still attached to it. It glided in, so it doesn't need its boosters to return to Earth. So this is a real problem. So how is new space debris created? First of all, we put it there, new objects, and collisions, causing these new fragments. So I'll give some examples, one of which will be very, very current with today's news. So in 2006, there was a Chinese weather satellite called Fengyun 1C. It was in a polar orbit, going over the poles, as lots of weather satellites do, and it's sun synchronous, which means basically the orbit was designed that the sun was always illuminating the Earth for taking good pictures of the clouds. So a run-of-the-mill, normal, ordinary weather satellite, nothing special at all. On the 11th of January 2007, Fengyun 1C was destroyed by a kinetic kill vehicle, which is an interesting term, traveling in a retrograde orbit at 8 kilometers per second. So if we have an object going in an orbit, we can put another object on exactly the same path, but go in the opposite direction, and they will collide. Okay? So this was done to Fengyun 1C by the Chinese as a test of, can we destroy a satellite? They destroyed one of their own, but this was a show of power, a show of force, and showed the ability to destroy a satellite. The problem with this, rather than being entirely needless, was that the Fengyun 1C was at an altitude of about 800 kilometers, so quite high, which means a lot of the debris won't burn up very quickly. So by the end of January in 2007, we can see in yellow here hundreds of new objects created. These are the fragments of that weather satellite. By the end of July 2007, we can see the debris spreading out. All of the yellow objects are from that one satellite. And by the end of the year, the debris has continued to spread, and we think about 2,000 objects, new space debris objects, were created by that one missile test. These are trackable objects, so quite large objects. If we look 2 years later, we can now see individual objects, some of them coming down, some of them going up. The orbit's spread out enough that now there's a chance of debris from one satellite hitting another piece of debris from the same satellite because of the spread of these orbits, because of the way they change over time. So this is an absolute mess. Okay? This is not what we wanted. So what did we learn from this needless military posturing? We learned that blowing up a single satellite can create a lot of debris, over 2,000 new pieces from that one missile test. On the bright side, though, I'm trying to be optimistic. I'm a positive guy. We know we can avoid this with 100% certainty if we can avoid launching any more missiles to do it. Okay? This wasn't an accident. We did it, so we can avoid it. Okay? So easy. No more anti-satellite missile tests. Now, there's some news today, so this is what's called foreshadowing. Right? It should be easy to avoid this mistake. So in 2008, there were 13,000 objects in orbit. 2,000 of those were from Fengyun 1C. So a significant proportion of all debris is from that one missile test. This shows the sensitivity of the system. Much more worrying are that some collisions are outside of our control. So in 2009, two satellites, Cosmos 2251 and Iridium 33. Cosmos was a dead Russian communications satellite going about its business. The Iridium satellites are what power the satellite phones with the big flip-up antennas that you see in spy films. So there's lots of them. And this was an active satellite. Iridium 33 was an active satellite. There was a warning that they'd come close together, but not that they'd collide. Okay. That warning was wrong. Okay. You can see the path of Cosmos here in pink, and you can see it collided with the Iridium satellite, and those objects kept on going in their respective orbits, but it was a side-on collision, an extremely rare occurrence again. But with enough objects there for enough time, you will get collisions like this. Okay, so this was outside of our control. Again, if we go through the year, you'll see the objects spreading out. This is because after the collision, all these objects have new velocities outwards that changes their orbits over time. By the end of 2009, again, over 2,000 new objects created by that one collision. So where are we today? Today, someone else got involved in the shooting down satellites game. India. So this morning, India announced that they had successfully tested their own missile to destroy a satellite. They had one of their weather satellites again, I think, and they destroyed it. Okay, knowing what happened with the Chinese tests, they went ahead. We don't know much details about this at the moment. We know it's at a much lower altitude, so it's not going to be quite as bad as a Chinese missile test because a lot of the debris caused will burn up. But some of that debris will go into higher orbits and might be there for quite a while. So you think you can avoid something until another country gets involved. Again, posturing. It's general election season in India. This is the Prime Minister showing that they're strong and tough. Okay. So that's not good news, but that's. I wish I could give you a visualization of it, but we literally don't have orbits yet for those new objects. They'll be generated over the next couple of days. So in 2019, there are more than 20,000 objects in orbit. And if we change our view to following the International Space Station, we can see how busy it's getting down in low Earth orbit. So again, all these objects are in their correct orbits. Again, you wouldn't see them like this. They're moving very quickly and they're very small, but it gives you an idea of how many objects there are. Multiple times a year, there's those warnings, there'll be a collision, are sent to the International Space Station, and they care greatly about anything hitting them, understandably so. So what happens is, if there's enough time, they'll do a small boost to get out of the way and hope they don't go into the path of something else. If they don't have enough time, all the astronauts pile into the Soyuz capsule, the life raft, spacesuits on, shut the door, wait for it to pass. Once it's passed, spacesuits off, go back into your business. This is a common occurrence. It's a real problem happening right now. Another anecdote I heard was the British astronaut Tim Peake was trying to get to sleep when he had just arrived at the space station, and it's apparently really loud because the air conditioning, all the machinery keeping these astronauts alive is loud, lots of buzzing and grinding. But when he was trying to get to sleep, he could hear pings, ping, 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 of small bits of debris hitting the outside of the space station. It's covered in lots of sheets of material to absorb those impacts, so there's no real danger from those small pieces hitting it. It's the same idea as a bulletproof vest. You can absorb a lot of energy if you cover it in enough material, but still worrying nonetheless. So what about the future? That's come up to the present day. Where's it going? What are we going to be trying to do about this problem? How can we clear it up? Is a common question. So we can start by trying to capture a satellite and drag it back down into the atmosphere. And we are testing the technology to do this. It's all very nautical. It's harpoons and nets, because that's what works for catching these sort of objects. But this is an absolutely valid research area, but it's not going to solve the problem. It can remove one object at a time, eventually, but there's still going to be 20,000 other objects. And these are only large objects. So you can imagine if there's a single dangerous satellite in a very bad orbit, we could remove it, but it's not going to solve the problem. What we need to know is where all these objects are to a much greater accuracy to work out what the danger levels are. Currently, we just don't know. The uncertainty we have around the orbits means that we don't know if collisions will happen. For instance, Cosmos and Iridium, we thought they'd miss, but they hit each other. The numbers were wrong. And we've got to think about knowing where these things are to far higher accuracy before we think about removing them with harpoons, however cool it might be. One thing we'll know is that we'll keep on using space for communications, for positioning, for scientific missions. Nearly all of our climate change data now that we have access to is space-based. Okay, so incredibly useful information. We are incredibly reliant on space, so we will keep on using it. But we also will come up with new uses for space. And some of these might cause more collisions because it's a numbers game. It's the more objects you have for a longer period of time, the more likely those collisions are. If you have a number of those collisions in a short period of time, you could get a chain reaction where those objects start hitting each other or other objects, which causes more objects, and on and on. And that's what we want to avoid. But it's just probabilities. So one thing that is being developed right now is satellite-based internet. So we all like to use our smartphones. We all want better and faster internet connectivity. And especially in the developing world, there's a massive desire for better connectivity. And a satellite-based internet system would offer this. So it would offer real benefit to humanity, but there is definitely a risk involved. This is because these constellations would have hundreds of new satellites. So OneWeb is one such constellation that is being manufactured now. The first OneWeb satellites have been launched. We'll have 648 new satellites in order to give coverage around the world. So currently, there's only about 1,500 active satellites in total. Okay, of that 20,000 objects, 1,500 are active. We're going to add 650 to that. But OneWeb aren't the only game in town. Not to be outdone, Elon Musk and SpaceX have their own plans for satellite-based internet, and their constellation has at least 1,500 new satellites, all in low Earth orbit. So there are guidelines and rules that these objects have to deorbit after 25 years, which they are following. But it's a numbers game. It's a number of objects for how long they're there. If we suddenly basically double or triple the number of large objects in this regime, in low Earth orbit, the risk goes up. Now, is that acceptable risk? We don't know. And that's something that I'll leave you with, is the idea that we constantly desire progress, and the use of space has enabled that from many different avenues. But is it worth the risk of one day losing it all and having no access to space? Thank you very much. Okay, questions?
Are there nuclear-powered satellites that we need to be concerned about?
So, not nuclear-powered in the sense we would think, but nuclear batteries are commonly used in space. So, for instance, the Mars rover is powered by a nuclear core. It's not a reactor. It's just used because it's a lump of metal that stays hot for years and years. There are lots of nasty things in orbit. There were nuclear satellites which involve coolant, so the liquid to cool the nuclear material. These broke, leaked, so there are perfectly formed spheres of frozen radioactive liquid flying around, which you do not want to encounter. So yeah, they're quite small, so they're not going to be the trackable size. But yeah, historically it was used in the period of, we're exploring, we're trying to work out what would work. Nuclear power sources we use. Nowadays we tend not to for obvious reasons.
You explained earlier how geostationary orbits are balanced exactly with velocity and altitude to appear to hang over one place on the Earth.
Yeah.
But the Earth doesn't just orbit, it also wobbles. Mm-hmm. How do the satellites adjust, if they do, for the wobble effect?
Yeah, that's a very good question. So, the rotation of the Earth. So mentioned briefly in my intro was my work previously in geodesy, which is the measurement of the Earth from space. And the Earth spins on its axis, but absolutely wobbles, and that wobble changes over time. It precesses in all sorts of very interesting ways. luckily in a small enough way and with a predictable enough time scale that the orbits, it doesn't really affect geostationary, basically. There'll be small changes, but nothing significant. It's significant when we're making very precise orbital measurements. So for scientific missions, we need to absolutely know the orientation of the Earth. But for the geostationary ring and for pointing our satellite dishes, the small error from not taking that into account, not moving these satellites around all the time, still means it's still within the beam, so you're okay. Great question.
You mentioned in relation to the SpaceX proposal, a rule requiring deorbiting after 25 years.
Yeah.
And that made me wonder about the broader context. Are there treaties that regulate what can be put up?
Yeah,
Are China and India in violation of those treaties? Have there been proposals? And do you think if there's not, or if there are, do you think that the treaties would be a way to deal with this problem or not?
So I try to be optimistic, but there have been lots of talk at the UN for decades about the regulation of outer space. And there's lots of guidelines, but no hard laws. There's no recourse around whose responsibility something is. Or if there is, it's never been tested in a court of law. So there's all sorts of talk around you have responsibility for your own satellites, but no one's ever been seen that through to its conclusion. All of these 25-year guidelines that are heavily pushed by NASA and the European Space Agency are just suggestions. Some countries now, you have to get a license to put an object into space. Apart from one startup in the States actually didn't and got in a lot of trouble. And as part of that licensing process, you have to meet those criteria. That's one way of enforcing it, but there's treaties, but they are basically flagrantly disregarded when it comes to a military context. And abided by only when private companies abide by them, only out of self-preservation. If SpaceX left the stuff up there for much longer than that, or added many, many more satellites, they'd be harming themselves. The risk would hurt them too. There's some self-preservation there. But the 25 years thing is something they're just saying, can they prove it? We'll find out in 25 years.
Hi.
Hi.
And this is about the satellite that was India just destroyed. So was it a operational satellite?
Yes.
And on a lighter note, if it was, now India won't know what the weather is?
So it was definitely an operational satellite. We don't know exactly which satellite it was yet. One of the contenders was actually a small communications satellite that was just launched earlier this year by India, only been up a couple of months. And now in hindsight, if it was that, it's all up in the air. So in a couple of weeks you can watch a video again and see how wrong I am. But put it up with the express purpose of being hit by that missile test. So they would have lots of sensors on it, lots of data coming from that to know exactly where it is, to see how successful the impact was, things like that. But it was their own satellite and put up quite recently, which is strange. Normally, they would pick an older, less useful satellite. So if it is that newer one, there's some interesting questions there about why put something up just 2 months later to destroy it. There's lots of unknowns at the moment.
How much did it cost?
These things are never cheap. It'll be millions and millions of dollars worth at the bare minimum. But in military context, that's a rounding error.
For your orbital analysis, what is the source or sources of your orbital elements?
Yeah, so this is a good question. I always like people. So I've got all these dots moving around. How do I know that? The only equipment, historically and mostly now, capable of tracking these objects is military hardware. Big military radar installations that were designed to detect if a nuclear weapon was coming over the horizon. They now have a secondary mission because they're still watching for those nuclear weapons. There's guys in bunkers constantly looking at screens waiting for nuclear weapons to come. But they've got to fill their days. So they also detect and track all these space objects to make sure they're not nuclear weapons. So all of this data used, all the historical data comes from the US Air Force, who graciously share it with the academic community. Without the data, I can't do my work. Okay? So there is a definite gift, but it comes with caveats, both stated and implied, in that the accuracy of the data is accurate to within a couple of kilometers position-wise. So I can show visualizations like this, and it's in the right place, but to know where something's going to hit something else, could be 4 kilometers away, could be a strike, we don't know. So the data is not as accurate as the data they actually receive. And in any data set, especially from a military context, there are omissions. There are things not there that we know are there because other people say, we can see the satellite at a certain point, and in this data set, it's like, nope, not there. So there's lots of military holes in this data.
Okay, I'm going to start up here and then come down because I've seen a lot of
Hi, thank you for the talk. The nano satellites, I don't know what the altitudes are and what problems they cause, but every nation seems to be getting into, the British. They're all trying to build systems that can take down trash. So, right, what the official explanation is like kinetic projectiles, small on cables to pull down trash. But aren't they also dual use? Couldn't they be used in an offensive capability too? So, are these really being tested for actually removing, deorbiting satellites, or are they being used to test something else?
We have a suspicious soul at the back of the room there, and rightfully suspicious. So nearly all the technology in use is dual use. Absolutely. The dual use has 2 uses. Dual use, sorry, my accent. Apologies. Has 2 uses, a military use and a non-military use. The remove debris, for instance, is a university-based thing. They are wanting to remove debris. But there will be lots of very interested observers looking at that research, building on it. Are the military doing their own work? Absolutely. There's work as well on on-orbit servicing. So basically going up and refueling satellites to extend their lifetime, which would help solve some of this problem. But if you have physical access to a satellite, that's also a weapon at that point. You can go up to a military satellite, and if you have physical access, you can basically get access to all the communications, encrypted or not, going through it. You can destroy things, you can create all sorts of problems. So all of these things have dual use. And it's just finding that balance of trying to make sure we're not making the problem worse by researching these problems. And there's a definite ethical consideration involved with that. But it's a tightrope we have to walk, basically. We want to remove these things. We have to develop the technology. Could it be used for something else? Absolutely.
Could you just say something about what are called trash or garbage orbits just above the geostationary orbits?
Yes, so the geostationary ring, if there's an object in low Earth orbit where it's very busy, we just give it a small boost and it burns up in the atmosphere. Objects out of the geostationary ring takes way too much fuel to bring them back in to burn up. So what we do instead is send them out to what's called a graveyard orbit. So try and send them out a bit further so they're in a nice circular orbit, not doing anything, just literally just orbiting around, which is a great idea. Until a couple of decades later, they come back. Okay, and this is imaginatively called zombie satellites, but basically that's not imagined. So objects that have been put in other orbits, they can come back in because of these sort of non-conservative forces, the force of the sunlight, etc., can push and change their orbits over long time scales. It's not going to come back quickly, but 10 or 20 years, 50 years, they can start coming back through and cause all sorts of problems again. So things that we thought were good solutions, putting them in these graveyard orbits, turned out to have problems involved.
Are there some orbits which are more crowded than others? For example, the ones where they put the satellites where they're always in sunlight kind of thing. So yeah. Those have to be a lot more crowded than some of these other ones. So doesn't the approach to eliminate the problem vary because of that? Absolutely.
So there's what I'd call prime real estate. And talking about the Fengyun 1C, which is in a polar sun-synchronous orbit is a super useful orbit. A lot of people want to be there. If you're a weather satellite, you want to be in that sort of orbit. So there are definite areas which are more crowded than others, and that's where any removal missions would have to quantify the risk given from all the satellites to try and remove the highest risk objects first. So you might pick some of the busiest orbital regimes and try and bring out the highest risk objects at a time. You wouldn't just choose any object at random. You'd pick something like some synchronous polar orbit or some other useful orbits. Judging that risk of which is the most dangerous satellite up there, that's a tough call because we don't know the long-term impacts. We can do lots of simulations of what's going to cause more likely collisions, but the uncertainty in our data means it's wide open. So we have to kind of make some judgment calls there.
Thanks. Is there any residual damage that's done if we were to bring down a lot of these? I mean, I know we talked about statistically it's hard to believe, or it's hard to hit a residential area, for instance. But as far as, like, we always say burning up in the atmosphere as if, okay, done and done, is there any type of problem with the ozone or any other thing if massive amounts of objects were to come down?
Okay, so there's a lot of mass in orbit, thousands of tons, but not enough to cause problems on that scale. But when we are bringing big objects back into the atmosphere, we have to be very, very careful. So there's a lot of work already thinking about how we're going to deorbit the International Space Station, because it's big and it's strong and large parts of it are going to survive re-entry. So we have to start planning now for basically how do we hit the middle of the Pacific Ocean, because that's the best place to aim. We've got a bit of room for error there, and it's nothing that size has ever been deorbited before. So for the last few years, you'll see on the news these automated transfer vehicles go up with the food and the oxygen for the astronauts and take away their trash. When those objects are full of the trash, as in the astronauts' waste, we are now deorbiting those in a slightly different way to try and get a feeling for how we might eventually deorbit the International Space Station, for instance, because it's these big objects we have to be very careful about. But large-scale effects, not really. There's not enough mass to disturb the system as a whole of the Earth.
With all this going on up in there, and all these little satellites and mini satellites and whatever else is going on up there, should be afraid that some of the stuff might hit the Van Allen belts or the ozone layer to really make a bad thing back on?
Yeah. Okay, so these natural phenomena like the Van Allen belts and things like that definitely affect our objects, but not vice versa. There's no real mechanism for these objects to dramatically or influence at all these natural occurrences, because the scale of the energies involved in these sort of global phenomena are so much greater than that involved with the objects. So they might be a threat to other objects and a threat to our access to space, but a threat to the environment, the Earth environment itself, I'd say no.
That's now.
Now. So always with the caveat. No.
So all of these objects right now are, I mean, they could be the size of a bus, but they could also be the size of a grapefruit.
Or bigger, yeah.
So how much stuff are we talking about smaller than a grapefruit?
Well, first answer is we don't know because we can't see it, but orders of magnitude more. So hundreds of thousands of objects in the 1 centimeter to 10 centimeter range, millions of objects smaller than that. It's the estimates based on sort of population studies, things like that, of the number of impacts on things like the solar panels.
So my second question is if we're doing spacewalks, I can understand we have, Kevlar vests and all that, but you can't see a human body taking a baseball at
it's not so
speeds.
There's no protection offered by the spacesuits to a space debris impact, basically, and it's a calculated risk. There's astronauts being up there in the first place is a calculated risk, but spacewalks you want to minimize as much as possible for a number of reasons, one of which being you are basically naked and exposed to anything like that. It would be like getting shot like a rifle bullet if a grain of sand size thing hit you. But again, you have to be very unlucky, but the more spacewalks we do over a long period of time, you might get unlucky. And it's at numbers. It might be vanishingly small. It might be once in sort of 1,000 years of spacewalks, or it might be once in 20 years of spacewalks. In which case, those guys and women will take the risk, but it is a risk.
Recently, Chinese announced that they want to put the solar panels in space, which is continuously running, and beam the energy down.
Yeah.
With this kind of a picture, I mean, I wonder how safe would that be?
Well, so it's a really interesting concept, and not a new concept, but the Chinese are kind of taking it forward. And the idea is to put large solar panels outside the atmosphere, they can collect a lot more energy, and then beam that down in a very tight beam down to Earth to be used for power. And this is a very green, renewable energy source, but comes with risks of very large objects in orbit.
Could that be in the geosynchronous orbit?
It could be. I don't know what the desired geometries, the desired orbits are for those power-type satellites. It might be, in which case there's different problems there. Is there room there? Is there going to be more collisions there? We use the geostationary orbits a lot. It's very densely populated. Is there room for these power satellites? So it's that trade-off of there's definitely a benefit, lots of green energy, but lots of risk. Basically collecting that amount of energy and beaming it down to Earth is an unknown, an unsolved problem as of yet.
I've seen your hand.
Do you know how many satellites are in geostationary orbit, how many slots are available, and who governs the placement?
So the exact numbers I don't have to the top of my head, but in the hundreds. And the slots are allocated and governed by an offshoot of the United Nations. The allocation process is Byzantine at best, but the idea is that because there's very definite areas and slots, you've got to stay in your area. And any deviation, you can lose that slot and they'll give it to someone else. And these things are worth billions of dollars. The satellites themselves are worth billions of dollars because they can be up there for 10, 20 years, constantly communicating with the Earth, making tens of billions of dollars of profit for the companies that launched them. So there's a lot of money involved in the geostationary orbit.
I was just wondering, in the future, when we're going to be trying to go to Mars, how will a space station, a spacecraft, get through all this debris?
Well, it's an excellent question, a very common question. So I had that question at lunchtime with the undergraduate students as well. And it's a numbers game. Again, if you're just going through this area to go out of it, you're actually exposed to the risk for a very short period of time. So you do a conjunction analysis, you see if there's anything obviously dangerous crossing your path, but the actual risk is quite low because you'll be through it and out of it in a matter of hours or days. It's when you're operating in this environment for years, that's when the risks build up. It's just where you are for how long are the two components to the equation.
Hi, I'd like to know if you have different satellites for cell phones, for GPS, for other important reasons. And I'm just wondering if you have something similar in air traffic control that manages all of those different satellites so they don't crash into each other.
That is a great question. So one of my research areas now is in space traffic control or space traffic management. And there is an analogy to air traffic control, but unfortunately it breaks down in the fact that we don't have active tracking of all these objects. Every plane in the sky beams out its location and communicates with the ground control, or with the airports. It's not the case in orbit. There are thousands, tens of thousands of objects that are not communicating, that are not telling us where they are. We've got to try and work out what they're doing, and they're not controllable. We can say to an aircraft on approach to the airport, okay, no, turn around, come back in 10 minutes' time. We cannot do that with space. We cannot move them around. We can move our active satellites, but we cannot move debris. So it's a real problem. It's a much harder problem to manage the space traffic.
Have you collaborated with Tim Floor or Rudy Yen of the European Space Agency?
Yeah, so I presented at their conference in Darmstadt a couple of years ago now. The community isn't particularly big, and we all try and work and share data as much as possible. European Space Agency have a dedicated space debris team who do excellent work. They develop their own models of where all these objects are. They sometimes have data on objects that aren't shared by the US military sources, so it helps fill in some of those gaps sometimes. And we all try and work together to improve the models collectively as a group, because this is a collective problem and it's a worldwide problem, so we try and collaborate as much as possible.
Hi, everyone. I've just recently finished reading the book Endurance by Commander Scott Kelly. He lived out there for a year on the space station, and his log is very, eye-opening. He mentioned things about how the space station is damaged from asteroids, so we have natural phenomena of asteroids. Now we have to deal with all the space debris. So now we're going to go up there and we're going to have people, actually astronauts fly to the space station on a commercial flight. So what do you think is the future for our health? Well, Commander Scott Kelly was exposed to all this radiation. He can't even, his cancer, all these health problems are going on for him. What is our future here on Earth with all these things happening? With the CAN satellites, with the students, all of it.
So we are more and more reliant on space-based assets for communication, for positioning, for timing. So lots of unintended dependencies on assets in space. If we were to lose access over a short period of time, it would be catastrophic for the world economy. But we'd survive. We'd just have to go back to how we lived in the dim and distance once upon a time, 1956. We'd have to just give up some of our creature comforts, some of the technologies and access we have. A lot of, so the GPS satellites we use for positioning, but they all work because they have atomic clocks in them. So they give very precise timing signals that are independent. And this is used by the global banking sector to time trades, to move money around. Everything's dependent on that space-based timing signal, because the idea is that no one can mess with it. So you trust a third party. If we were to lose access to GPS, and we'd lose the blue dot on our phone, but we'd also lose the world economy. We'd recover, but we'd have to take a step back and rethink. And then if there was a chain reaction and we lost access to certain orbital regimes, that would be the status quo for a long period of time. The timescales for the natural change in these things is very, very long. So we'd have to come to terms with our new reality if the worst happened.
Dr. Grey, you did a great job of explaining some complicated things to make them sound understandable.
Thank you.
What puzzles you? Is there anything you don't understand?
The more research you do, the less you understand. That is absolutely, as I've gone through my career, I know less and less and less. What puzzles me, it's the approach to research sometimes. So the problem as I see it as a researcher is, where is this stuff? So we know to within 2 kilometers away, but I need to know where it is. I'm used to working on scientific missions, which were cooperative, and I could, as a group, we could work out where they were to within a few millimeters at any given time. We don't know where this stuff is. And what puzzles me, but what aggravates, maybe the wrong word as well, is that we don't, if we knew where this stuff was, we have the models to work out where it'll be, and we could solve the problem. We could avoid it. But we don't have that information. What is a problem is that some people have that information. Commercial operators have their own information of where their satellite is. They don't share it. Different countries don't share their data. So the big problem and big thing that puzzles me is how to make countries and commercial entities with a shared interest, apparently, cooperate when they haven't been cooperating for years. And that is a problem that transcends engineering and comes down to it comes down to the humanities. It comes down to persuasion and cooperation and a collective outlook on the use of space. So that.
All right. This is probably a silly question, but so over the year, I mean, the ISS is a special situation. Like it's permanently manned, so it's probably the most significant object that has to be guarded. And over the years, like tons and tons of trash have been loaded into spacecraft, into transport craft, and burned in the atmosphere. Mm-hmm. So again, it may be silly and may affect the orbital dynamics of the ISS. But have they considered instead keeping the trash and building it around the ISS as shielding?
Yeah. Well, you could. You lose some of the aesthetics of the of the thing then, but you absolutely could. And there's a large amount of the effort and energy goes into getting these objects into orbit. Anything you can do once you're there to reuse it in any manner would be a fantastic use. And there's that sort of sustainable use of trying to refuel spacecraft, reusing things again, design them for reuse, make modular satellites is a definite area of research, is a real strong area of research right now, because you use all that money and energy to get it there, make use of it in multiple ways if you can, recycle it if you can. That sustainability is definitely on the cards now. That's a good question.
Thanks for giving me something else to worry about.
Yeah, well, I've got to share the worry.
Now, am I right in saying there's no friction in space?
No friction. Yeah, there is friction between objects in space and the atmosphere, but once you're above and outside the atmosphere, there's no friction.
So there's a possibility to be perpetual.
Yeah, perpetual is a strong word. It's like saying infinite, but so geostationary orbit, for instance, is very far and away from the Earth's atmosphere. Although there are still a few rogue molecules around there, but not the friction as we would know. Those objects, if we all disappeared tomorrow, those objects would be there in thousands of years' time. Yeah. They would just keep on going. Some of them would be pushed around, as we talked about the graveyard orbits and the zombie satellites and things. There'd be movement, but never enough to bring it close enough to the atmosphere to burn up. So things out there, they are going to be outlasting all of us, outlasting our civilization, who knows?
I'm just thinking the effect like plastic, for example, that it's breaking down into much smaller particles consistently, and then then you have a problem that's a huge problem.
No, that's actually a really interesting point. So out at geostationary orbit, you've seen probably satellites covered in what is a gold foil. And this is insulation, basically, you manage the temperature. And it's like mylar foil. And over time, it degrades and spalls off, especially and these sheets start their own orbits. And there's a big amount of work actually done with some of our European colleagues on how these pieces of foil move, because they don't act like normal objects in orbits, because their area is much, much greater than their mass. So they get pushed around by those photons a lot more. So these things can go really weird orbits. And it's just down to the breakdown of the materials over time, over decades, because we're talking about long time scales here. It's just basically the foil just comes loose and slowly drifts away, and then that foil is just a bit of foil flapping around until it goes into the wrong orbit and then comes and hits you at a few kilometers per second, and then it's a problem.
I was wondering about the flipping of the magnetic poles. How is that going to affect the satellites? And a gentleman just mentioned about trash. I had read something about before that they could use trash to use as shielding for the when the astronauts are going to Mars, and maybe, I guess, as they go into deep space, they could also use it for shielding.
Absolutely. So to your first question, the magnetic poles, so we're talking about non-conservative forces. There's a hierarchy, and drags at the top, then our solar radiation pressure. Something we looked at in our research group in London when I was there was the Lorentz force. This is a force, if you remember back to your physics at high school, of any charged particle moving through a magnetic field. There's lots of right angles involved. Okay, fields of force. And certain objects, their orbits can be changed due to the magnetic field. The actual flipping of that it's not going to happen overnight, and there'll be no overall net effect probably to the orbital elements. It's because of Lorentz force, the forces due to the magnetic poles will be so low. The effect down here on Earth of the magnetic pole switching might be a bit more dramatic, but in terms of the orbital elements, not a big impact. Going to Mars, away from the magnetic field, is an unsung hero of Earth. It protects us from all sorts of nastiness, radiation mainly, out in the solar system. And once you get away from the influence of Earth's magnetic field on the way to Mars, for instance, you're exposed to a lot more radiation, dangerous amounts. And shielding is important, and you can line your spaceship with lead, or, if you're sensible, you can line it with lead, and also, as you produce waste, or have a dense object, so if you're taking soil, for instance, to grow plants, you put it on the outside, so you're protected from that radiation, because it's a real risk. Astronauts going on a return trip to Mars will be exposed to a lot of radiation, and it's something that a lot of the work on the space station has been to try and gauge the body's reaction to these long-term exposures and trying to work out if people will be in any fit state to operate when they come back. Thank you.
Okay. Are we fit? No more questions? Really last one.
Is this image available online? Is the motion image right now available online?
This one itself is not. I'll be recording a screencast. I have a number of videos showing the progression over time of debris. If you just search for it. Yeah, absolutely.
Thank you, everyone, for coming out.
Thank you.